So in a dynamic language, if you want to do polymorphism, something you can always do is you can simply write a function which looks at its arguments, looks at their types, looks at the number of arguments, and decides, based on that, I'm going to pass these arguments onto this other function. Basically, the function would act as a dispatch to other functions, and that way you would achieve polymorphism. To support this style, Clojure introduces a special kind of function called a multi-method, which is explicitly for this purpose, for the purpose of dispatching to other functions based upon the type and number of the arguments. Multi-methods are just more convenient for this purpose of polymorphic dispatching compared to regular functions because, well, for one thing, say you can add new methods to which to dispatch such that you don't have to define every single possible dispatch function in one place. You can spread it out through your code into different files and so forth. So there's reasons like that why you would want to use multi-methods. A few times in passing, I've suggested that functions can actually take a variable number of arguments. Such a function is called in Clojure a variadic function. It's called variadic because the term arity refers to the number of arguments which a function can take, and so a variadic function is a function with a variable arity. Despite the fancy name, it's really just the same idea as what in Java are called var args. So in the parameter list, the symbol ampersand is actually treated specially. Effectively, you can't have a parameter named ampersand. Rather, when you precede the last parameter with an ampersand, that means that it's a variadic function, and that parameter is the parameter which receives the extra arguments to the function. So here the function with the parameters x ampersand y, that function can take either one argument, in which case that argument will be passed to x, and y will be nil, or it can take two or more arguments, in which case, again, the first argument is passed to x, and then any remaining arguments are passed as a vector to y. Similarly, a parameter list of a, b, c, d, ampersand d means that the function can take either 3 arguments or 4 or more arguments, and if it's just 3, then those arguments get passed to a, b, and c, and d is nil. But if there are 4 or more arguments, then the 4th argument and all the arguments after it get passed as a vector to d. And finally, I should make clear here that unlike some dynamic languages like, say, JavaScript, where you can pass any number of arguments to any function and it's not going to cause a problem, it doesn't throw an exception, in Clojure that's not the case. If you pass the wrong number of arguments to a function, it'll throw an exception. Earlier, I may have given the impression that the reader syntax consists entirely of just literals and also maybe the semicolon to denote comments, but in fact there's a bit more to it than that. There are additionally about a dozen different syntactical conveniences. Rather than explain them all, I'll just go over one here, and that's the apostrophe. You can use an apostrophe in Clojure, and in fact in most objects of Lisp, as a reader syntax for quote, for the special form quote. So where we see here I am quoting the symbol George with the special form quote, I can instead simply put an apostrophe on the symbol George. Or say, rather than fully writing out the quote special form around this list here, I can simply precede the list with the apostrophe. And what the reader does is it simply looks at this apostrophe and automatically encloses the thing it precedes in the quote special form. So come evaluation time, it's exactly the same as if you did in fact write out the special form quote. Var, as we've already seen, is mainly about storing the global things of our code, such as, say, all the global data structures and all the global functions and so forth. What I haven't explicitly explained yet, though, is why vars are mutable. Normally in a program, our function definitions and our data type definitions and, say, our constant variable definitions, those globals, those things don't change in the course of a program. So why are vars mutable? Well, because they are mutable, it then allows us to take a running system and patch it. We can say, take a buggy function and we can replace it with another function, and all doing this while the system is still running. How useful this is, well, it really depends on your domain of programming. There are programmers out there who work in domains where bringing down a system is a very costly choice, and so anything you can do to just keep the whole thing running, that can be a lifesaver. Most programmers, though, don't ever have many real-world opportunities to use this feature to change the running code of a program as it runs. On the other hand, the ability to change the code of a running program could potentially be extremely useful if you can work it into your development process, because it can enable a more hands-on and experimental way of coding. At the start, I briefly mentioned that Clojure has a number of much hyped features which allow what some people call lockless concurrency. Simply put, the big idea is that Clojure has these three mutable reference types. That is, three types in addition to the var type, which we've already seen. These three types are called ref, agent, and atom. And what makes them different from vars, and what makes them different from each other, is that they each have a unique semantics as pertains to concurrency. These three types have different rules, different restrictions about how they are mutated. I won't explain all three, I'll just talk about refs. Not that agents and atoms are complicated, in fact, refs are the complicated one, which is why I'm going to try and explain them. So the idea behind a ref is that it is a mutable reference which can only be changed in a transaction. The concept of a transaction you're probably familiar with from databases, and the basic idea there is that a transaction is a unit of work, a section of code we can say, that deals with a set of data, and the rule is that if during this transaction the set of data is modified by some outside source, the transaction should fail, meaning everything done in the transaction should be undone. It should be as if it never happened. Then the transaction should be reattempted, but now with the updated data. But again, if during this transaction the data is modified by some outside source, then again transaction should fail. So as long as this critical data is being modified outside the transaction while the transaction is running, we're just going to keep retrying the transaction. It's not until finally during an attempt of the transaction that the data is not modified by some outside source, it's not until then that we finally commit the data. That is, the changes to the data made inside the transaction are finally pushed out to the whole system, such that it becomes what successive transactions get when they access the data. Now, Clojure actually enforces that refs only get modified in transactions by throwing an exception if you attempt to do otherwise. So what this looks like in code is you simply use the standard library macro called doSync. doSync takes a body of expressions which make up the transaction, and then in the transaction, that's where you can call the operation that modifies a ref. So the way it works out is this. We have different threads running, and in those threads you might have different transactions, and those transactions might overlap. Well, if two overlapping transactions both modify the same ref, one of those transactions is going to attempt to commit before the other one. And it's the one that tries first that's going to win. The other one is going to have to retry. Understand that there are two criteria of the scenarios in which we want this behavior. The first is that we require a consistent view of the data for some duration of code, and that duration is the transaction. The logic in this code requires that we get the data at the start of the transaction, and then if anything happens to the data, it's something we did to it, not some outside source. We don't want it to change out from under us. So the transaction gives us this consistency. But on top of this, the second criteria says that if the data is modified by some outside source during the transaction, then whatever we're doing in the transaction is no longer any good. We have to give up and try again. Just be clear that not all shared data requires this restart behavior. For those cases that do, though, that's when we use a ref. Also understand that because transactions are automatically retried and you don't know how many times they're actually going to run, it's generally a mistake to do any input-output work in transactions.